Hello guys, this is Mr. Leshin and this is one class physics. In the previous class, we started our discussion. We started talking about surface tension, which we explained very, very well last week with some little experiments. Telling you that surface tension is a force that tends to make the surface of a liquid act like it's an elastic skin. It tends to make the surface of a liquid act like an elastic skin. And the surface tension will give an insight whereby you see an insect walk on water like they're walking on sand or walking on a solid, but they are walking on water. So due to the fact that their weight is lighter than that of the water or denser to that of the water, but they walk on skin and their legs are stretched on the water. So they're standing on a solid or something like a skin. So the force that tend to make that happen is called surface tension. That is the force that tend to make the surface of a liquid act like a skin, the compactness of the water, of the surface of the water. Like even another insight whereby you have a very early, or probably you didn't close your tap very, very well. See, the water from it acts like a bubble that can hold something together, but it's a bubble. But when the weight of the water it's much, it drops down and bursts. So these are the effects of what surface tension. We gotta talk about the application whereby we talk about the waterproof materials like the raincoat, the umbrella, the tent that prevents water from dripping into it. And we talk about how you can reduce surface tension. How you can reduce surface tension probably by like that of the waterproof material. If the water is dripping on it and you touch it, then you tend to break the water, the compactness, and water touches your hand and falls through the waterproof material. Probably in water, you can adding a detergent to water breaks the surface tension. Boiling of water breaks surface tension. Adding alcohol to water breaks surface tension, and more like that. I think I even gave an assignment that you should even research for more ways by which you can reduce surface tension. But this week we continue from where we start. Is also an extension of the surface tension, but we're looking at capillarity. And under this capillarity, we're looking at that kind of force, two types of force between molecules, which is the cohesive force and the adhesive force. Cohesion and adhesion. We call them the cohesive force and the adhesive force. These are the two kinds of force that tend to act between molecules or atoms. So this is what we'll be looking at in this week topic. So let me share the notes with you and the lesson objective. So this is the week 8 physics SS1 capillarity. And under capillarity, we'll be looking at the cohesion and adhesion. So this is our lesson notes. At the end of the lesson, students should be able to define and explain the action of capillarity. It's also the same action of capillarity is also the same as capillarity. So we have defined and explain the action of capillarity. What does capillarity mean? So we look at this. And number 2, explain cohesion. This part of the force and how it applies. What does it entails? What does it mean? And the third one and the last one, which is explain adhesion and its application. I already told you the two kinds of force that operate between molecules are called cohesion and adhesion. So what's the difference between the two, or is there any similarity? So let us look at the explanation of the first one, action of capillarity. So capillarity, let us look at this experiment which we are familiar with. When we dip 3 tubes with fine bores, but with different diameter, when we talk about diameter, the surface, the length of the surface, into a clean water. You can see these are 3 balls, like let's say 3 tubes. One is very, very tiny, and this one is more, it's a bigger than the narrower one, and this is the biggest. We have 3 tubes. Please let me add the spotlight to it so you can get it very well. So follow the arrow, please. This is 3 tubes, one, the tiniest. This is bigger than that, and this is the biggest. So you notice when we dip 3 tubes, but different diameter into clean water, yes, we observe that the water rises in the tube, but the narrow the bore, the higher the height to which the water rises. Yes, look at the experiment very, very well. You can practice it at home. Add 3 tubes, like probably 3 different sizes of tubes. The narrower and the and bigger ones to it. You will notice that water rises in the narrower than the other tubes. Water rises in this one than the other tubes. So this is one part of the experiment. Let us consider the note before I explain for that. And another one says, if the experiment is repeated with soap solution, that is a soap water, similar situation will be observed, but the level of soap solution in the tube are lower than those of the water. That is, if you repeat this experiment but not with, this is ordinary water experiment, but not with ordinary water, but a soap solution, is a detergent solution, a soap content, then the water will also rise in the narrow tube than that of the what are bigger ones. But the level at which the water will rise, the level it will not get to this level at which water rises in the tube. It will be a bit lower than it, but in a similar what situation. So another experiment says, another experiment, if however the tubes are deep in mercury, another solution, but mercury solution, the mercury falls in the tube, it doesn't rise. Mercury will not rise in the tube. Mercury will not what rise in the tube, but it will what fall even below the what the water surface, the mercury surface. Mercury will even, it will even be low. It will not rise. You can see the water solution rises above the water level here to this length, making it showing that this is the narrower, the next one, and the other one, the bigger one. But water rises. But in the case of mercury, it doesn't rise. It falls what below the level of what a mercury solution. So mercury falls in the tube. The mercury level is depressed below the level of mercury what outside what the tube. The level of mercury in the tube, the one in the tube falls below it, that it doesn't rise. The narrower the tube, the lower the what the mercury level. The narrower the tube, the lower the mercury. You can see it's a different situation than that of the water solution. Please take note of this experiment very, very well. Water rises in tube, but it now depends on the what and the diameter of the tube. The narrower the tube, the higher the water rises. But in the case of mercury, the narrower the tube, the lower or the more that the mercury will depress. So we are here. The action of liquid to rise or fall in the capillarity is known as what? Capillarity. So this is the definition of capillarity. That is the tendency of a liquid to rise or fall in a narrow tube is called a capillarity tube. It's called what? Capillarity. And it's also known as what? The capillary what? Action. That is the tendency of a liquid to rise or fall in a tube. In a capillary tube is called capillarity. And you know the reason why? I will now look at the reason why water rises and what mercury doesn't rise. Water rises and mercury doesn't rise. Look at this note extension. It says in both water and soap solution, yes, the surface of the liquid curves upward. That is in the concave shape. Look at the shape. You can notice this probably when you are drinking your soft drink. Put your straw deep inside inside your soft drink or inside the bottle. You notice that it will rise above the level of the straw will rise above the liquid content. You can practice that, and the shape of it is like this. It's a concave shape. It curves upward. There, noting that it is rising upward. It gives the definition or the description that is it rises upward. You can try that and notice your straw in your soup. It rises above the liquid level. But in the case of mercury, it curves downward. It curves downward away from the glass. So you can see this is the mercury content in a beaker. Let's say in a beaker, and this tube, two tubes are placed in it. You can see the narrower the tube, the lower that the mercury depressed or falls, and you can see this one is a bit higher than the narrower tube. But in the case of water, the narrower the tube, the higher by which the water rises in the capillarity tube. These are the effect of capillarity action. This is the effect of capillarity action. So why does water rises and mercury falls? We'll look at that as we continue in the topic. So these are the two. I told you earlier that these are the two kinds of force that happens that operates between molecules. One, the cohesion. Cohesion means that this is the force of attraction. They are both force of attraction between molecules. But this is the force of attraction between molecules of the same substance. Force between molecules, that is the force that tends to operate between molecules of the same substance. We talked about that in the last class. I make mention of it. And e.g., molecules of water. You can say the molecules of water tend to bind together. The force of attraction between molecules of water to stick together is called the cohesion. While adhesion is the force of attraction between molecules of different substance. Between molecules of different substance. The force of attraction between molecules of different water, e.g., molecules of water and that of glass. That is why you see that we explain further. I see when you sprinkle water on glass, it tends to stick on it. It tends to stick on it and wet the glass. Water remains on glass for a longer period, unlike mercury. mercury does not wet glass. You might have been taught that in your chemistry, but mercury does not wet glass. So these are the effects by which all these things upon the cohesive force and the adhesive force. I take again, the cohesive force is the force of attraction between molecules of the same substance, while adhesive force is the force of attraction between molecules of different substance. Molecules of different substance. Let's go. So cohesion and adhesion, look at this. Let me explain this very, very well. Cohesion and adhesion explains the different action of water, water and mercury when spilled on the clean glass. It explains why glass water wet glass and mercury does not wet glass. If mercury is sprinkled on the glass, it slides down together. It doesn't wet glass. It doesn't scatter. Unlike water, when you sprinkle it, it scatters but stick on the glass. But mercury, on the other hand, it doesn't wet glass. It slides, seeps down or creeps down the glass. One, because the adhesion of water, that is, the adhesion force is the force of attraction between different molecules. Now, when water is sprinkled, that's what I'm going to explain now. When water is sprinkled on a glass, the adhesive force is the force between different molecules. That is different substances. That is the force of between water and glass. They are different substances. So because the adhesion of water molecule to glass is stronger than the cohesive force, then water spreads out on the clean glass surface when sprinkled in it and wet glass. Yes, the only reason why water wets glass is because the adhesive force, the force of attraction between water and glass, is stronger than the cohesive force between the water molecule. I believe you understand that. That is, the adhesive force overpowers the cohesive force of the water molecule. That is why water spreads wet glass. That is not the case of mercury, which does not spread or wet glass. That is, the cohesive force of mercury, the bond, the force of attraction between mercury is stronger than the force of attraction between the mercury and the glass. So then it stands for creeps down the glass. It doesn't wet glass. It's always together. The mercury falls at the same by which it's sprinkled on the glass. Look at the notes. The cohesion of mercury is greater than the adhesion of mercury molecules to that of the glass. That is, the force of attraction between the molecule is stronger than the force of attraction between the molecule and the glass. So as a result, mercury forms into a spherical bead on the glass surface and falls. That is why mercury doesn't wet glass. So we go to the next slide. So cohesion and adhesion, as well as surface force, tension forces, are responsible for the capillarity of liquid. That is capillarity, the rise and fall of water or liquid in the capillarity tube. So cohesion and adhesive force are also responsible, and also the surface tension force are responsible for this capillarity action. So water wet glass tube spreading a thin film of water on the inner surface of the water tube. This is what we explained earlier. That is the reason why water wet glass is because the adhesive force is stronger than the cohesive force. The cohesive force is the force of attraction between the water molecule, but the adhesive force is the force of attraction between the water and the glass. So the adhesive force is stronger than that of the cohesive force. That is why water wet glass. Adhesion of force causes water to creep up inside the tube. The adhesion is now the effect by which water rises in the inside the tube. I told you is the force of attraction between two different substances. That is the reason why, because the adhesion force is stronger than the cohesive force, then water tends to move in the tube or in the porous surface. The water is held up as it creeps by the surface tension force acting on the circumference of the surface of the liquid. The water does keep rising in the tube until the weight of the water draws up in the tube balances the surface tension. Water will continue to rise until its weight balances the weight of the water or the surface tension acting on top of the column of the water. It gets to a point where it doesn't continue to rise. That is, there's a balance at that point. But the reason why water tends to rise in the tube or in the porous way is because of the adhesive force between the substances, the two substances, is stronger than the cohesive force. But in the case of mercury, it is not like that. The cohesive force of mercury does not rise in glass. It drops down. That's why you have a convex shape at the surface of the surface of the mercury. You can see the shape. It drops down. while this is what a concave, which what it rises up. Water rises up what in the what in liquid in what in a glass to brother. So let us look at the next slide. It says, this then water, it's not in only glass soup that we have this effect of cohesion and adhesion. There are so many examples, even in our daily life, that we notice very, very well. Look at the first one. Other examples of what capillary action. You can see if we talk about the capillarity, that is the action of capillarity, the tendency of liquid to rise or fall in the capillarity tube. You can see the rising is we talk about that in water experiment and what soap content experiment, but it falls in what where mercury tends to fall in the capillarity tube because of the cohesive force is stronger than the adhesive force. So let's look at these examples of capillary action. That is capillarity. We all know what a blotting paper is. Take example for let's say your tissue paper. You're familiar with that, your tissue paper. When you pour, when it soaks in water, just a part of it tends to soak in water. You can see that water then continues to rises till it soaks everything, till it continues to soak all the tissue. But probably a smaller part of the tissue paper is soaked in water. But then when water tends to rises, this is the fact of this is the effect of adhesion stronger than the cohesion. I told you the force of attraction between what are different substances makes the water rises, and the water tends to rise in the tissue paper. So these are actions of blotting paper. An example of blotting paper are the tissue paper, your filter paper, and thereabout. Most many fine pores, they have, they are porous. They are porous. The little holes in the blotting paper function as tiny capillarity tube. Ink and other liquids rise through fine pores and enable to the blotting paper to soak up the liquid. The pores in your blotting paper gives opening or the opening give rise to the liquid, and it tends to soak up the liquid. You can say this is the effect of capillarity action. Water tends to rise in your tissue paper, or ink also tends to rise in your tissue paper. Another example is the rising of oil. Probably you have a lantern in your house. You can see that when your lantern, the wick, the thread, you soak it in kerosene, and all of a sudden you see that the kerosene rises up in the wick, rises in the through the spaces, the holes in the wick. This is the effect of capillarity, the rise of liquid in the wick. So the rising of oil in the wick of lamp through the spaces between the common thread which make up the wick is another example or effect of capillarity. Another example is the absorption of water by a towel. The absorption of water by a towel. You can see the towel tends to soak up water. It's soak up water through the fine pores in in towel. So these are the effect of the rising of capillarity actions, rise and fall of liquid in the capillarity tube, or in the porous materials. So this is what we'll be looking at in our in this topic, that is the capillarity and the cohesion and the adhesion. We all know why liquid rises in water and liquid rises in capillarity and mercury forces. The example is why liquid wet glass and mercury does not wet glass, because the adhesion force of water is stronger than the aggression force of water and glass is stronger than the cohesive force of the water molecules. You can say all these daily experiments we've seen in our daily life are due to the effect of adhesion and cohesion. When the adhesion force is higher than the cohesion force, that is why liquid tends to rises. But in mercury, it is different. Mercury's cohesive force is stronger than the adhesive force. You can take this experiment and get a tissue paper. A tissue paper with a porous, put one end get a 2 glass of cup and fill the capillary to fill it up and put the tissue paper and spread, cuff it into two. That is, one end tends to be in the liquid here, and one tends to be in the other cup with empty. Leave it for hours. You see that it will be after some hours. See that the liquid, the tissue paper soaks up liquid from the glass cup with water into that which without water, and the other cup tends to fill with water also. That is, place your tissue paper into 2 cups. One filled with water, the other not filled with water. cuff it, that is the tissue paper falls in the water here, and the other end of the tissue paper is in the what empty cup. After some hours, you see that the other cup without water tends to what be filled with what with water. So these are the effects of what capillarity and what adhesive force and cohesive force. It is an extension of what our previous class, and we from today are end of the what surface tension, capillarity, and what and the other forces that tends to act what between what are molecules. Molecules of the same substance is cohesive force, and the molecules of different substances what is adhesive force. On your note online, I've sent some note online. Under the note online, I told you to what the assignment is what give other examples of what capillarity action aside from the what blotting paper, the tissue paper I mentioned, the oil wick in the lamp, and also the towel being soaked up what by water. With this explanation, I believe you'll be able to what go or look into what more of the daily activities that you've seen before, and also and see that it is what related to what to the topic, and you'll be able to what answer the what question. Read the notes and go through the video once and again for better what understanding. Thank you for your time. Have a blessed day.